Okay, we're starting Unit 2 on the derivative. I'll print you one of these so you can have like a header for your notes. The derivative, differentiation, and derivative rules. That's where we're starting. The third unit will be more of an application type of thing. But I think Unit 1 was the longest one we have, so we should be able to go through these a little bit better pace. But here we go. The first thing we're going to talk about is the definition of a tangent line. Okay, so we need to talk about a tangent line. And I love this up here. This little paragraph is pretty cool. If you recall, a tangent, especially with a circle, is what you did in geometry. Touch that circle at one point. Okay, well, but when the curve is not a circle anymore, we have a couple of situations where that can occur. This situation here, the Q, is not considered a tangent. All right, at P it is, and so I like this note here. It says a tangent to a curve is a point at a point is a line that best models or approximates the behavior of the curve at that point. So this one, as this curve is heading in this direction, its tangent line would do a similar thing. It would head in that direction too, but linearly rather than curving like this one is. And what's happening here is we had a little hill, we started going down the hill, and at that point then our line should model that behavior of sort of going down that hill, a negative slope there. And then as we came back around, we would have a positive slope, and so and move it on up. Okay, so I love that. It's kind of a definition, all right, but it's more of a she says a better way to describe the tangent line. All right, so that's good. So then if we can do that, then we can find the slope of this red line using calculus. Now, at first, we're going to just have a particular point that we're going to deal with, and this point. Oh, okay, yeah. I'll say this and I'll come up here. That point that we're going to talk about, where it models the behavior of the curve at that moment, is the point of tangency. And in this case, and all of the work that we're going to do on this lesson, it will be at A, comma F of A. All right, and then this is big. The slope of that line will be denoted by, and this is a notation we're going to use the rest of the year. So this is big, right here. All right, F prime of A. F prime of A is going to be the slope. So the slope of that line right there will be called F prime. Okay. Any function with a defined slope at a specific point will have one and one only tangent at that point. Yes, because we'll just have one line that's going to model, and we're looking for the slope of that line, and it will be called F prime. This is big. All right. Now, also, we could call it the slope of the tangent line. We could call it instantaneous rate of change. And we can also call it the derivative. We will use all of these things interchangeably. They all mean the same thing. The slope of the tangent line means instantaneous rate of change. And then the derivative is the calculus word to represent that situation. Okay. All right. Awesome. Okay, now, and we've done this before. The very first lesson of the year was about average rate of change. Okay, so we're gonna get a little practice on that again. The average rate of change, and what you probably realize we're going to do is we're going to try to take that red line and find the instantaneous rate of change by having this point approach that point. That's the goal, and so I'll show that in the next section. Okay, but for right now, just a little practice. And I like the notation here. So it's the average rate of change is going to be your change in your y's over your change in your x's. Y2 minus 1 over x2 minus x1. Same thing you've done for years and years. And they're going to call that the slope of the secant line, because this now is a secant line that hits twice. And then here we go. So f of b, this is y2 minus y1 over x2 minus x1. All right. Now, and so once again, we have an equation we're going to use. And so we're going to substitute in. So the average rate of change is equal to, all right, in this particular case, f of 3 minus f of 1 over 3 minus 1. Okay, so nothing new here. You've done this before, but we need to kind of practice it again because it was the first lesson, and so and now we're back to it. So f of 3. All right. So f of 3 would be what? 27 minus 9. 27 minus 9. Okay. And then f of 1 would be 1 minus 3. There we go. And then that would be divided by 2. And so we have 18 minus negative 2 is just 20. And then 20 over 2 is 10. Very nice. Okay, good. All right, and so now, so that would be the slope. And I know this is not the same graph as x cubed minus 3x, but we could graph that real quick if you want to. Desmos, x cubed minus 3x. All right, and so we just found the average rate of change from, what was it, 1 to 3? Yeah, 1 to 3. So from x equals 1, right here, to x equals 3, which is way up here. So that slope right there of that tangent line, let's see if I can draw it. So from x equals 1, good, to x equals 3, which, it might be off the screen there. So we just found the slope of that line. There's no way I'm going to be able to draw it very well. I'm going to give it my best. Let's try again. This line right here, that line. Nobody says how thick it has to be, right? Okay, that's it. Okay, so that would be, that's 10. All right. Oh my gosh, that was terrible. Sorry. Okay, so back here. Okay, so that's it for example 1. All right, next we're going to talk about moving those 2 points together, the Q and the P, close together so that we can approximate then, or maybe do even better than that with limits to find exactly what the slope would be at a particular point. Okay, that's coming next.